My name is Kate Woodland. This is Physics 2211, Lab 2, Motion of a Falling Object. In this lab, we were asked to analyze an object that is falling straight down. The object was dropped from rest and falls somewhat slowly. This lab looks at the effects of gravity and drag, both separately and together. I found data from the real world using Tracker and also formed two different computational models using GlowScript. This lab will demonstrate an object falling with acceleration because Fnet is not equal to 0. Here are the formulas used throughout this lab to create accurate computational models. It might be a little unclear which v-average formula to use in the position update formula, but it's actually not too complicated. When we only account for gravity, Fnet is constant because only the one force is being applied. When the force is constant, you typically use the formula v-average equals v-initial plus v-final divided by 2. But because we are applying Newton's second law computationally, we are going to say that v-average is approximately equal to final velocity. When you consider both gravity and drag, Fnet is constantly changing because the drag force is getting bigger as the force of gravity remains the same. In this situation, v-average is approximately equal to the final velocity as well. I also use the velocity update formula. The only thing that changes when you are considering just gravity or both gravity and drag is the value of Fnet. In the case of just gravity, Fnet is equal to negative mass times g, with g being Earth's gravitational constant value 9.8 meters over second squared. When considering both gravity and drag, Fnet equals the gravity force plus the drag force. The drag force is proportional to the square of the object's speed, or turbulent drag. B represents the proportionality constant. We use speed instead of velocity because vectors can't be squared, but scalars can be. The drag force is positive because it points in the opposite direction of the object's velocity. The system for this lab was a light pink ball. The surroundings were the Earth, the meter stick, and everything else around it. I imported my video into Tracker, set my axis as the purple coordinate system, y is the horizontal, chose my time frame to be between the two black triangles at the bottom, making delta t equal to 0.6 seconds, and tracked the ball's position around 15 different times. This produced the position versus time graph seen on the right. Because the graph isn't linear, we know that velocity wasn't constant and the object experienced acceleration and a non-zero net force. Here's a diagram to help show the net force on the object when only gravity is considered. The initial conditions for the computational model with just gravity are the ball's mass, 0.025 kilograms, position, 0.002914 meters in the y direction, and velocity 0, setting j hat equal to 0, 1, 0 will help us show the direction of the force. B is equal to 0 to show we are not considering drag for this model. Like I previously said, Fnet is equal to the force of gravity, and our time frame is 0.6 seconds. Here is the position versus time graph produced. As we can see, it is not linear. And then here's the diagram to help show the net force of the object when both gravity and drag are considered. Fnet will equal the two forces added together. For the computational model with both gravity and drag, most of the initial conditions remain the same. The ball has the same mass, initial position, initial velocity, and the time frame remains the same. I set the proportionality constant b equal to 0.03. I found this number through the plug and chug method until the position matched the real-life position found through Tracker. Fnet is now gravity plus drag. The other thing that was changed was the aeroscale value. This was found by dividing distance by weight, where weight is equal to mass times g, or the magnitude of the force of gravity. And here's the position versus time graph produced. Here's a graph with the observed position, the position found with the gravity-only computational model, and the position found with both gravity and drag. As you can see, the real-life data lines up more closely to the predicted model with gravity and drag, implying that drag did play a role in this experiment. The model with just gravity shows that the object would have traveled a greater distance than it actually did. Here we see the velocity versus time graphs predicted by the computational models. The graph on the left shows the velocity when only gravity is considered. In this scenario, Fnet is equal to the force of gravity, so the system has a constant acceleration of negative 9.8. This acceleration is demonstrated by the negative linear slope of the graph. The graph on the right shows the velocity when both gravity and drag are considered. In this situation, the object's acceleration is constantly changing until it hits terminal velocity. Terminal velocity can be seen at the very end of the graph when the line begins to straighten out horizontally. Terminal velocity occurs when the object is no longer accelerating, implying that Fnet is equal to 0. With our two forces, this would mean that terminal velocity would occur when the force of gravity and the drag force are equal. Remember, force of gravity is pointing down and the drag force is pointing up. The object would then fall at a constant speed. If the object was thrown downward instead of dropped from rest, the terminal velocity would still remain the same. The terminal velocity actually isn't dependent on the initial velocity of the object. It depends on the object's mass, surface area, density, and the medium density it is falling through. None of these factors change, so terminal velocity doesn't change. This can also be proved through graphs predicted by the computational model with both gravity and drag. As you can see, They both end at around negative 2.75 meters over seconds, but they started at different velocities. The graph on the left started from rest, while the graph on the right started at negative 1 meters over seconds. Overall, we learned all the components that go into the motion of an object falling. The acceleration and therefore velocity of the object depends on the forces acting on it. We saw the differences in velocity and position when we focused on just gravity compared to when we analyzed both gravity and drag. This lab shows the importance of considering all forces acting on your system. Thanks.